of electricity. Okay, so what we are trying to figure out in this position, or what we're trying to find out in this slide. So we have to identify what are the probable problems, or what are the possible causes that using electricity may cause to us. Will it harm us, or will it, and if it does, so how is it going to do that, and how to prevent that? That's the main problem. That's the main idea of the whole system. That not only that we want to understand what could be the major causes or what could be the problems, we also want to understand how to prevent them. So we are going to first understand what are the problems, and then we're going to look at the preventive methods or the preventive measures, how to stop that from happening. Okay, so let's start with the first one. So damaged insulation. I'm sure that we are very familiar with this type of wires. We see that with irons, we see that with vacuum cleaners, we see that with, most probably, with the charging wires that we have for our phones. I'm sure that we're familiar with that. Have you seen this type of wires around the house? Or have you seen this condition? So that is known as a damaged insulation. And this is problematic because it exposes the live wire. Okay, so in our chapter, or in this topic, what we have done is that in previous lessons, what we used to do is that we had the positive terminal and the negative terminal for the DC supply, or the DC battery, or cell and power supply, whatever that is. In this chapter, we are dealing with an AC supply. Now, in AC supply, one wire that brings current to the appliance is known as live, and the wire that takes the current away from the appliance is known as the neutral. And in common layman terms, if let's say you have an electrician over to your house and he's working with the electrical appliances, he may call the live wire as hot wire and the neutral wire as the cold wire. You see, this is how the common electrician or the common layman speaks with each other. But in physics, or in actual, you can say proper terminology, that will be live and neutral. So the definition of live wire is that it brings current into the circuit or into the appliance, and the neutral wire takes the current away from the appliance. Okay, so the damaged insulation, what would be the problem? So the problem is that when this wire actually carries both wires. So inside of this, we have the live wire. We also have the neutral wire. The live wire is taking the current towards the appliance. For example, you may have connected a bulb over here, right? And there is a switch over here, and we have an AC supply. So this is how the wires are actually connected, right? Okay, so it's possible that the live wire is taking the current towards the appliance, and the neutral wire takes the current away from the appliance after it has been utilized for its energy, or electrical energy. Now, it's possible that when this insulation breaks down at this location, it's possible that this breakdown of insulation may cause one of the live wires to be exposed from one point. And then again, it's not necessary that it's going to give you an electric shock, but we are anticipating beforehand that this may happen. So if somebody accidentally, without caring about this, actually touches this piece of insulator or broken insulation, and that broken wire is actually the live wire that is actually broken, that will give an electric shock to that respective person who's operating that machine. So this is a hazardous condition. We need to avoid this, and if you see that a wire looks like this, immediately replace it. Okay, so the next question, or the next danger, is the overloading of sockets, and that leads to the overheating of the cables. You see, all these cables that you have with your appliances, they're designed for that specific appliance. They can carry a certain amount of current, but they cannot exceed that limit. And it's not about the limit of the conductor per se, it's actually their thermal limit, the heat limit that they can sustain. This insulation of the plastic, the insulation on the wire itself, and the thermal capacity of the wire that we are using for that situation, there is a limit to that. And why do we say that there is a thermal limit? You see, if this wire is designed to carry 2 amperes of current, and you ask this wire, or you demand 10 amperes of current through this wire, it may be able to sustain it for a very short amount of time, but soon, very quickly, this will heat up and eventually melt, which is going to cause a short circuit. What is a short circuit? We'll get to that later. So it's a bad idea to overload the sockets, which will overload the cable that actually brings current to the socket. So if you demand a lot of appliances or a lot of current from the same socket, that is a bad condition. That's a hazardous condition. We should not be using appliances in such a way. But of course, there are in terms of real life, there are certain situations in which we can use it. You see, one receptacle what is a receptacle is this one plug that you have in your house that you can use with a switch, right? They are typically designed from 5 amperes to 10 amperes. If you're just going to charge your laptop and your mobile phone and you're just using small peripherals, then you can connect more than one appliances. But again, by the end of the day, it is not advised, not recommended at this point. If you install a lot of appliances on the same receptacle, you demand a lot of current, so the wires that actually do bring current to the receptacle, they would eventually overheat, and that would lead to a short circuit. The insulation will melt, live may come in contact with the neutral wire, and of course it will cause a short circuit, which may lead to house fire, so it's a bad idea. Again, damp conditions, we are very familiar with that. We must not operate electrical appliances near damp environment. So the two most vulnerable places where the damp conditions do exist, one is the washroom and the other one is the kitchen. So in the kitchen, we are usually washing the dishes and we are operating with the electrical appliance, let's say dishwasher, microwave, and let's say some baking oven or something like that. So we must not operate those machines with damp conditions, or let's say if your hands are wet, it would be a bad idea to operate them. So the better way would be to first dry your hands, wear some shoes to increase the insulation or at least have more resistance with the ground, and then you may be good enough, or you may be a little eligible to operate the appliance. But then again, it is not advisable. It is just a necessity condition that's possible, but not advisable. If you do have to use, let's say, appliances that are used basically in the washrooms, for example, a hair straightener or the automatic toothbrush, the electrically operated toothbrush, although that is a very small appliance, it doesn't cause electric shock. But then again, so if you have to operate any device, it's a good idea to bring that device out of the washroom and then just operate it in the dressing room where you have the mirror in your room. That would be an appropriate place for that. So again, damp conditions provide lesser resistive paths, current flows through the body and will cause an electric shock. So these are the key ideas or key problems with the dangerous use or dangerous activity, you can say, or the probable dangers where electricity can be a problem for us. Now, how to prevent all of this, how to see that if these conditions do exist, what are we going to do? Okay, so the first one that we have is a short circuit. So what is a short circuit? First, let's try to understand that. Short circuit is high flow of current. High flow of current. Why? Due to reduced resistance. You see, this is an accidental condition. We are not doing that deliberately. Some students take away from this lesson or the lecture that probably we are doing this on our own, because when we are discussing how it happens, students think that we are doing this deliberately. No, we're just trying to identify that this may have happened, which may have led to this idea, and it's all based on speculation, of course later verified. Based on speculation, we've landed on this idea that this is why electric short circuits do take place, and let's try to prevent that. So first we need to understand why do they take place and how it actually takes place. So what happens is that, for example, we have an AC supply with live and neutral wire, and let's say this is a bulb or an appliance, an electric heater, air conditioner, whatever we are using at that point, even a vacuum cleaner. So the live wire is bringing current into the appliance, and just the way that we've seen damaged insulation, it's possible that during the damaged insulation or in the damaged insulation, since all of the wires are damaged, it's possible that the neutral wire is also damaged. So the live actually accidentally comes in contact with the neutral wire. If the live wire actually comes in contact with the neutral wire, the bulb had some resistance to offer to the electric current. Let's say it could be 10 ohms. Now, if the wire is in contact with the next wire, the resistance of wires is effectively zero. So if you're operating at a voltage of 220 volts, for the sake of understanding, let's say that the resistance of the wires is 0.01 ohms for this complete path. the live to bulb and bulb back to the neutral. So if I had to find the current in this situation, I would have used V equals to IR, and 220 volts are available to me. Current is what I want to find out, and the resistance is 0.001, and if I take that over there, the value of current is going to be very high current. This is a short circuit. How do we name, how to remember this with the name? So the current has found a shorter path around the resistor, so it is bypassing that path, flowing through the neutral back to the supply. Why is it not wanting, or why is it not trying to flow through the resistor? Because when we look at this in this term, we see that it provides an alternate path to the current. The current reaches at this point and sees two paths being in parallel. So one path is through the resistor and one path is through a path which the resistance is virtually zero. So all the current prefers to flow through that path and ends up creating a short circuit condition. Do we understand this point? Again, this is based on speculation. This is based on our assumption that this is what may have happened with the appliance. But of course, the condition is very real. That what is the consequence of this probable condition, the short circuit, that's very real. And this is not a good condition to be to leave your appliance in. That is the primary cause, 100% the cause of house fires that are actually initiated by electrical or faulty electrical wiring. Anyways, let's try to see how to prevent this, how to prevent this short circuit. You see, since this is a very high flow of current, if I had a device that could interrupt that could disrupt the flow of current after a certain value, then that would be able to help me to stop this from happening even when we are not looking at it. So we have two devices in our course. The first one is the fuse and the second one is the circuit breaker. Circuit breaker. You may have seen these appliances in your house. Let me show an image to you. So this is what a circuit breaker looks like. You may have seen this in the distribution box outside your house or inside your house when you actually enter the house. Have you seen such a thing?
Yes.
So these are actually circuit breakers. And if you see closely, if I zoom into the situation, their respective current ratings is actually written on the box or on the front. You see, this is G20A. That would mean that this is 20 amperes worth of breaker. And this is G6A. That would mean that it is 6 amperes. G is just a letter for their universal ranking, that what type of breaker they are, right? That's not important. The value with the A is important. A is a unit of current, and 20, 10, 16, 6 and so on and so forth, they are the actually current ratings that they are good for. If the current through them exceeds 6 amperes, they will trip. And that actually tells us that, okay, if the circuit breaker has tripped or if it has switched off, that means that room for which the circuit breaker is installed may have a short circuit in one of the places. Do we understand this point? Right? So even when we are not looking at this, even let's say you're sleeping, you're not always keeping a check on the electrical wires. So this appliance or this instrument actually, or this object actually keeps a check and balance on that respective side of the circuit. That even when no one's looking around, we must be able to prevent this condition from happening. So let me zoom out back. Okay. So so this is what a fuse looks like. Previously, they were used in place of circuit breakers, but due to the advent of technology and newer methods, we don't use fuses anymore for the house, but we do use them for electrical appliances individually. So for example, if we have a laptop charger, if we have a phone charger, if you have an electric heater, an air conditioner, or any appliances that are working on individual basis, one-to-one basis, right? They do have a fuse installed inside of them, right? So not only that we have installed a circuit breaker at the back end, we have also installed fuses inside the appliances. So we are adding another layer of safety. They're not required, but it's a good idea to put them there in the first place. Because sometimes what happens is that when you're operating your own appliance, for example, laptop charger, phone, baking oven, or UPS, or any device like this one, it's possible that it may cause an electric shock to you while you're working on it, right? So to stop that from happening, what we've done is we've installed a fuse in their path, So if a person accidentally comes in contact with that machine and is going to eventually observe an electric shock due to high value of current, these fuses will actually melt themselves and provide a safe passage, or you can say just cut out the supply and keep the person who's going to operate the machine safe. Now, a fuse is just a piece of an electrical wire connected between two terminals. I have deliberately designed it to be a wire. Why? Because wires have low resistance. So what I'm expecting in return is that since it has low resistance, the moment the current exceeds a certain value, this piece of wire, due to low resistance, will heat up so much that it will eventually melt and sacrifice itself to protect the rest of the circuit. Do we understand how the fuses are doing this job? Right? So this is just a piece of wire. They are sacrificing themselves. They will themselves become heated up. Just a moment. Okay, so they will sacrifice themselves and heat up and melt the wire, right? Okay, moving on to the other side, we have these circuit breakers, and they are also doing the same job. But where do we install them? How do we use them? So basically what we're doing right now is that, let's go back to the, okay. So the symbol for the fuse is the piece of wire enclosed in a container. The symbol for the circuit breaker is this one. That is the universal symbol for the circuit breaker, and this one as well. But they are not included in your course. I've just communicated this to you, or just shown these symbols to you, that if you go to a higher level, you will see these two symbols are representative of the circuit breaker. Even for the diagram for the house, you may find that this is how the circuit breakers are represented, and this is how the fuse is represented. Another alternate symbol for this is basically like this one, but again this is an obsolete one, or you can say it's an older one. Alright, so how do we install the fuse and where do we install it? Okay, so we will always install the fuse in the live section of the wire that brings the current into the circuit. We will never install such an appliance or such a protective equipment in the neutral wire. We will always install them in the live wire. Reason being, for example, in this case, which is the correct way around, the fuse melts for, let's say, due to a short circuit. The fuse has melted, right? Okay. The fuse has melted, and now the circuit effectively has broken down from between them, right? So there is no current flowing. Now what I've done is I've disconnected the live wire with the appliance. So even if a person comes close to the appliance and there is some exposed wires or there are damaged insulations due to that appliance or around that appliance, this person who's operating it will not get an electric shock because the live wire is not connected to it, right? It is completely isolated, and the person effectively, whatever it does is connected to the neutral wire, right? But if the person had connected it into the neutral wire and nothing in live wire with the bulb, so let's say under a short circuit condition, the appliance would have been prevented, or you can say the appliance would be safe. But after breaking down the fuse, we see that the connection is broken, right? So this is my neutral wire, this is my live wire. If a person comes in contact with this appliance, I can see that my connection effectively is with the live wire. I'm still connected to the live wire, right? And I'm not connected to the neutral wire, which is the cold wire, which has no electricity. So this is a hazardous condition, that even after installing the fuse, I have saved my appliance, but I still not have included the safety for the operator. Again, we are anticipating, we are expecting that if the fuse has blown, if the fuse has melted, then it is safe to work on this machine. But if the person has installed the fuse in the wrong place, then whoever mechanic or whoever operator comes close to repair the machine will not know in his own consciousness that whether the machine is actually off or whether the fuse has actually cut me off from the live wire or not. Do we understand why we connect it in the live wire and not the neutral wire? Because live wire would mean complete disconnection with the live wire, but that has the high voltage. So the person who's actually coming to operate on the machine will always be carefree. He doesn't need to check the switch again and again. He doesn't need to check whether we're connected to the live again and again. He would just expect this to work, that he's safe to operate on this machine. Do we understand this point?
Yes.
Alright. So Okay, so moving on to the next part. So that is where we, and similarly, the circuit breaker will also be connected in the live wire. So I'm adding this point over here, always connected in the live wire, right? Because again, we're anticipating that the person should be safe, or the person who's going to come to this place should be safe. Okay, so moving on to the next part. Now we have the installation of circuit breakers and fuses done, and we have done all of that. So we have done circuit breakers, we have done fuses. Now we move to the correct placement of the switch. Now the switch should also, the simple switch that we have in the walls should also be placed in the live wire. And the reason is the same, because if this is the AC supply and this is the live wire, right, and this is the appliance, what we want is that the switch, circuit breaker, or even the fuse, what we want them to do is a complete disconnection from the live wire. So we will always introduce a switch in the live wire. So even the switches that are installed in your house or in your room that operate the lights or the bulbs or the fans or the air conditioner, those switches are connected first with the live wire, and then they're connected to the appliance. So when you press the switch, this is what actually happens. So the live wire actually gets connected to the neutral wire, because if I look at here, I'm still getting a carry on of the neutral wire up to this point, right? So this is the safest condition where the switch should be placed. It will always be live wire. Then we have a 3-pin plug and then the earth wire. Okay, so what does the 3-pin plug look like? I'm sure that we are familiar with that. Okay, so this is what a 3-pin plug looks like. Are we familiar with that? Do we know what that is? Right? So why do we need that is because two pins are, one of the pins is responsible for the live wire and one of the pins is responsible for the neutral wire. This is what the appliance will use to operate successfully, right? But what is the work of this third pin? This third pin is known as the earth wire. Now, what is the earth wire? Let's try to understand that. So again, the earth wire is there as an anticipation. The problem may or may not be there in the first place, but anticipating or expecting that it may happen soon or later in life, it's a good idea, or it would be a good idea to place that in the first place. So what are we doing right now? Okay, so we have a live wire, we have connected a switch, we have a fuse in its place, so I'm adding all the security stuff over there, and then we have the appliance itself like this. So most appliances that we operate on our daily basis, they are enclosed in a metal container. Let's say the washing machine, baking oven, microwave, all of them are enclosed in a metal container. So it's possible that sometime, again, based on an anticipated accidental condition, it is possible that sometime later in life, because we're constantly using the wire, it's possible that due to the bending effect of the wire, due to its own stresses, it's possible that it undergoes, you can say, damaged insulation problem. So if that damaged insulation problem occurs, the live wire may come in contact with the metallic part internally. You may not be able to see this from the outside of the appliance. It may happen internally. Now again, if this happens, you don't know that this has happened. So if the operator comes close to the appliance and touches the metal part of the object, you may have experienced this sometime in your life, that you get an electric shock from the metal part of the appliance. Why has that happened? Because internally the live wire has accidentally come in contact with the body of that metal appliance. This is why you will see that we are now shifting towards plastic bodies for most appliances where we can. The washing machines and all of them are having plastic bodies, because that adds another layer of safety, because plastic is a poor conductor of electricity. So even if a damage condition or damage situation occurs for that respective person internally, we can still prevent that person from getting an electric shock. The primary objective is to save the person. The appliance comes second. Okay, so based on this accidental condition, what I'm going to do is I'm going to deliberately provide the appliance with an alternate path for the current, because I don't know when this is going to happen. So I'm going to connect a third wire with only the body of the appliance and connect it straight to the ground. What we do with this third wire in real life is I bring that third wire back along the neutral wire and then bring it back over here, and I connect it to the 3-pin plug that we have. So one has the live wire, this one has the neutral wire, and the third pin has the earth wire connection. So do we understand how we're connecting all the 3 pins of this 3-pin plug? Right?
Yeah.
So let's understand, and of course this earth wire in the distribution box of the house that I have over here, the distribution box of the house that I have over here, they will connect this third wire, the earth wire, through this display box to the ground of the earth. Where is the ground? The literal ground, the dirt, or you can say the pavement outside your house. That is what we're calling the ground. So I will just bury this wire into the ground, and there is of course proper technique to what depth it should be buried to, according to the size of the house, how many points should there be. So this is what we're doing right now. Okay, so what happens if this condition arises? If a person has installed this third earth wire in the house connection, if this condition arises that internally the live wire becomes in contact with the metal part of the object, then what's going to happen is that this path that we provide to the ground has a resistance that is much lower, let's say 0.1 ohms, and the person who's going to come near this operating machine has a resistance approximately of 500 ohms, for the sake of example. So the current would prefer to pass through the wire rather than passing through the person. Even though if the person is not operating the machine, still the current is not going to pass through the appliance. Why? Because the appliance has a resistance of approximately, let's say, 30 ohms. But the earth wire and the metal body, they have a combined resistance of 0.1 ohms. So instead of passing through the appliance, if this insulation breaks down internally, the current will flow through the live wire, encounters this metal part or metal body which has a lower resistance, then encounters this resistance that has another lower resistance path, and it will flow to the ground. And again, when this condition happens, the resistance is very low, so it will create a partial, you can say artificial short circuit condition, because the resistance is low, so it will cause a high flow of current. When the current flow increases, that would eventually cause this fuse to break down or to be blown, right? And when the fuse is blown, it actually breaks the circuit. So when the operator comes close to the machine and tries to close the switch on and off again, the machine won't turn on. Then he will know that either the fuse is broken down or either there is something wrong with the appliance. So he will open up the machine, see whether the fuse is damaged or not. If the fuse is damaged, that means that the appliance is experiencing a short circuit. If the fuse is not damaged, that means that there is some actual problem with the rest of the circuit, right? So it can be worked on. Do we understand what is the purpose of the earth wire and the extreme condition that if something like that arises, the fuse will melt because of the high resistance, right? And even if the person tries to come in contact in such a situation, the current would prefer to pass through the earth wire, saving the operator who is actually going to come accidentally in contact with that situation. Do we understand this point?
Yeah.
So this is the complete protective circuit for just one appliance. That is how we use, or that is how we're supposed to use an electrical appliance in our house, apart from being careful about the damp conditions and all the rest of the things that we're actually being careful about. Okay, so we have done for today the 3-pin plug. We understand where the earth wire is supposed to be connected, why, and double insulation in certain appliances. I just talked about that over here, that today washing machines are coming in, you can say the plastic bodies, right? So that is a double insulation case. Even the fans, the ceiling fans that we're using right now today, they may have a metal outer body, but internally they are double insulated by wrapping the core or the winding of the fan in paper, in thick paper or in cardboard, so that it adds another layer of safety and security to prevent it from an electric shock or to create a short circuit. Similarly, most appliances that you will see around you, they are now preferred to be designed in plastic bodies, because we want to protect the person from getting electric shock. We can sacrifice the appliance if it dies or if it just malfunctions due to the short circuit, but we cannot sacrifice the human life. So we will put everything or every effort over there to first prevent the human person or the operator being safe, and then as a secondary measure, If we can do something about it, we will install such a circuit that it eventually stops. You can say it eventually also saves the appliance from getting damaged any further, right? So do we understand how these 6 measures are taken for the maximum safety or safe usage of electricity? Do we understand this?
Yes, and double insulation just to
Let's look at this question to see what's the best condition or best way to connect all the circuits. So the fuse has to be in the live wire. This is live and fuse. Okay, best. But we don't have the switch. We have the switch after the appliance. It would be better to connect it before the appliance, right? So this option will be rejected. If we come to this point, we have the switch in the live wire, but the fuse is the neutral wire. So this is being rejected because of the fuse. Then we come to the option D. The fuse and the switch both are in the neutral wire. Absolutely wrong. The switch and the fuse is supposed to be in the live wire, right? So fuse and the switch are in the live wire. So the best answer or the safest option will be option C, right? Okay. So this is just a summary of what we've done today, and just looking at one more question over here. Okay, so the switch is supposed to be the live wire. So W is the live wire, right? And this is what goes in and completes the circuit, comes out again. X should be the neutral wire, right? Because we need to complete the path. And the wire that is actually connected with the body only and is brought out separately is the earth wire, right? So option B would be the best configuration to use these wires. Do you understand the type of questions? Right?
yeah.
Okay, all right. So you can see this is a double insulation using a plastic body over metal appliances. Okay. This color code was a part of the course previously, but now it's not. But I will recommend remembering this as general knowledge. In real life, the yellow-green wire, the yellow wire or the green wire, is actually the earth wire. And universally, right? And the brown or the red wire is usually the live wire as a sign of danger. The blue and the black wire are usually the neutral wire, right? So wherever you go, this is what every engineer or scientist, or you can say a mechanic, is following. You can see that over here. This brown will be the live one. The blue will be the, the blue will be the neutral one. And they have actually connected this in the wrong way. This is the fuse. The fuse should expect the live wire first. So this brown wire should have been connected over here and the blue wire should have been connected over there. Do we understand the problem, right? So the first current, or the current when it enters the switch, must encounter the fuse. So this is the live wire. It encounters the fuse first and then goes to the appliance. Similarly, the blue wire represents the neutral wire and the green yellow represents the earth wire. These are universal color codes, not a part of the course anymore.